All right, yes, I welcome everyone to our class this morning. We are all in class and that is good. At least for the first time, everyone has been able to attend the class on time. Everyone has attended on time. You've come on time and that is good. Hope that we keep the spirit high as well. So in the last lesson, we looked at mechanical properties of matter. And what we're seeing on the screen right now is simply a summary of what we've looked at so far. And at the moment, I believe that all of us can at least define what density is. We can define density and first calculate some numbers concerning density. We know what force is, pressure. That pressure is the force over area, you know the SI unit of pressure. You can at least derive this expression here of pressure in fluids. And we looked at Hooke's law. We carried out an experiment, and we said that when we come back to school, we shall need to do some experiments as well. And at least for now, we have an idea of what Hooke's law is, what we do experimentally, and to solve some numerical questions as well. Then, we introduce ourselves to Young's modulus, whereby we looked at what stress is. We did some computations here as well. We looked at what strain is. And one thing to remember is that when you're calculating the strain here, so that always pay attention to the units. Always pay attention to the units of extension and the length. We looked at Young's modulus finally, whereby we say that Young's modulus is the ratio of stress to strain. Then we also looked at some calculations concerning Young's modulus. And we ended the lesson by commenting briefly about the work done in stretching an elastic material. And I hope that by now we don't have any complaint as far as this is concerned. I was expecting that you get some more numbers from the end of chapter questions. That is on page 111. And from any other source, the internet has a variety of these. Simply search for topical questions on properties of materials. You'll find them. And we should keep reading, we should keep revising such that we stay up there. We're looking for that point there, that A, that grade, that's so great. So that is what we looked at yesterday. Maybe a quick recap about the energy stored in a material. This is what we said. This is what we said, that in case we have an elastic material, for example, a rubber band. Some of us left early yesterday, some 2 minutes to time, some of us left. So in case we have an elastic material like this of original length L0, and this material is stretched by a force F, and as a result it extends. It undergoes an extension of length E, that is our extension. I can even call it X, there's no problem, like that. So we said that initially before you stretch, our force F1 is equal to 0. When you stretch it up to a given length, up to this point here, our force F2 is equal to 0. Is equal to F. Is equal to F, like that. And from the definition of work done is equal to the force times the distance. In this case, we will be looking at the average force. Average force times the distance moved in the direction of the force. And this is the same as 0 plus F out of 2, then times our distance, which is the extension E. So this will give us a half F times E. That is the work done in a stretched elastic material. And we said that from Hooke's law, F is equal to KE. We can as well substitute for F in that expression there, and we say that our work done is the same as a half KE times the E, which is the same as a half K E squared, and that is what we have here. The X is the same as the E. So that is what we ended with, and you need to do more calculations on this. Get time, get these questions, and practice. I'm going to send you some. You identify your mistakes, and we stay good. Okay, so tomorrow we shall be having our lesson on Firefly. That's what I'm saying. I was muted. That's why I didn't pick some of my comments here. So we shall have our lesson on Firefly, and I'll be able to send you some more about this. Please, when I send, do these numbers, send them.
Mr. Hakim is having network issues.
Sure, I've got some internet issues.
It could be the power.
Can you hear me now?
Yes, sir.
Yeah.
Okay, that's good. That's good. The internet is on and off. That's why you're not able to pick me, but what I've done is simply to... Okay, so we've looked at this, and please, I'm expecting that I don't like, I asked the first time, was there any problem that you found as you're doing some more questions, and the reply was just no. So hopefully everything is good. So today we want to look at another topic or another chapter, and that is waves. That is waves. So today morning, this is what we're going to be looking at, waves, and we look at our syllabus. Look at our syllabus. So I'm hoping that everyone can see clearly what I am showing you right now. So I'm saying that in this topic of today, waves, we are supposed to be looking at what progressive waves are. And in this lesson in particular, we're going to be looking at what a wave is, some of the terms that we use, for example, the wavelength, the frequency, the periodic time, the amplitude, etc. And we must be able to derive this expression here. We call it the wave equation. V is equal to lambda f, and to use it as well. So that is what we're going to be looking at today in this topic of waves. So just give me a minute here, and then I present my slide to you. Okay, let's begin our lesson by having a look at this video here. Person has left. Okay, let's pay attention to this video and be asking some questions to you as well.
We're all familiar with waves, especially water waves. But sound...
Can you hear the audio? Hello? Tamale, Amu, Ayush, can you hear the audio on this video here?
Sound and light are just as wavy, and they're even more common. Luckily, we can learn a lot about sound and light waves by looking at water waves. Here are some continuous circular waves being made.
Yes, members, can you hear the audio? I need to get an affirmative from you.
Yes, sir.
Yes, sir, but the video seems not to be playing.
It's kind of breaking.
Okay, it's fine.
We're all familiar with waves, especially water waves. But sound and light are just as wavy, and they're even more common. Luckily, we can learn a lot about sound and light waves by looking at water waves. Here are some continuous circular waves being made by a point source as shown from above, so that we can see their crests moving outwards. We can also show the waves side on, where it's easier to see what's making them. For example, here a rod is being dipped in and out of the water. How would you describe a wave to a friend? We can describe the waves using their wavelength, which is the distance between their crests. It's also the distance between their troughs, because this is the same distance. We'll call the wavelength lambda, which is a letter that stands for L in the Greek alphabet. Now we'll fade out the overhead view and just look at the side view to make the waves look simpler. And here's a boat to show some of the strange properties of waves. How is the boat moving differently to the wave? Notice how the wave is moving left to right, but the boat only moves up and down. You can check this out next time you're in a boat. The speed of a wave is how fast it's travelling from left to right here, and is usually given the symbol V, which stands for velocity. Velocity is another word for speed. Notice how the speed of the wave is constant, and each crest moves at the same speed as the others. But the boat's up and down speed changes, and you can see that it's moving fastest in the middle of its cycle. This cyclic type of movement is called simple harmonic motion, and we'll cover that later. A pendulum is another example of simple harmonic motion, although it moves horizontally instead of vertically. The amplitude of a wave with symbol A is how high it moves up and down compared to a flat, calm surface. High amplitudes are caused by the source having more energy and dipping further into and out of the water. The guy on the boat would notice that he would rise and fall more, so he'd get a more energetic ride. The wave's frequency, given the symbol F, is the number of waves being made each second. The frequency is also the number of waves passing by the guy in the boat each second. Here, only one wave is passing per second, so scientists say that its frequency is 1 Hertz. Hertz is the unit of frequency, and it just means waves per second. It's usually shortened to Hz. This unit was named after the famous German scientist Heinrich Hertz, who proved the existence of electromagnetic waves, which we'll explain in another video. Interestingly, Hertz was not only a clever scientist, he could also speak Arabic and Sanskrit. Both of these languages are steeped in scientific and mathematical history. Does anything happen if we increase the frequency by dipping the source in and out more often? Let's double it from 1 to 2 Hertz. Looking at the wavelength, we can see that it gets shorter. We double the frequency and the wavelength looks about...
Mr. Hakim, it's breaking completely.
Yes, please, you're saying?
So it's the same thing on my side.
Yeah, same thing everywhere.
This means that when frequency increases, wavelength
Yes, what is energy?
Ability to do work.
The ability to do work.
Ability to do work. Very good. Now, in this video, what we have seen is that as someone is moving that stick into the water, in other words, the person is dipping an object into the water continuously, like we have seen in this video here. That person is doing some work.
We're all familiar with waves, especially water waves. But sound and light are just as wavy, and they're even more common. Luckily, we can look at the waves being made by a point source, as shown from above, being dipped in and out of the water.
So we can see this person here doing some work. This person here doing some work using an object like, it can be like a stick, it can be like a stone, it can be anything that you dip into the water continuously. In other words, even if you throw just one stone into the water, it is going to form those ripples, moving from the center where that stone has fallen, moving outwards. Now, all that energy there is not going to stay in one position, and you can see that energy is making the water to move up and down. And that's why we're talking about the ripples or the waves. When we check clearly here again, we can note this. We can note this. Just a moment, then I show you. At this point here, you can see something.
It's moving left.
What we are seeing here is a person or an object, like for example, someone who's doing skating. This person here is doing some skating there. And what we note is that the person is moving up and down, just like the water itself, the water medium. But at the same time, we're seeing that the ripples are moving from one end going to the other direction. Meaning that when you're talking about a wave motion, in other words, wave motion involves a transfer of energy from one end to the other without motion of the water medium itself. You can check it again here and you see.
To right, but the boat only moves up and down. You can check this out next time you're in a boat. The speed of a wave is how fast it's traveling from left.
Okay. So after having defined what energy is, we're saying that energy is the ability to do work. We are looking at now waves, and we're saying that in a wave or wave motion in general, it involves simply the transfer of energy from one point to the other, but without transferring the medium itself. That is what we need to know about this. And you can begin by writing this in our books. Somewhere, just simply write waves. Waves. Or in brackets, wave motion. And then you give me the definition. Definition. Who can repeat it? Who can repeat it? What have I said? How do you define a wave?
Hello?
Yes, Tamara, we're hearing you. Tamara, you want to say something? How do you define a wave? Or anyone? Hope that you can hear me, members. Hope that you are through with this. So, a wave is a disturbance in a medium in which energy is transferred from one end to another without transferring the medium itself. Without transferring the medium itself. You can also do that table there. We have the mechanical and then the electromagnetic waves. So what is the difference between the two? What is the difference between the two types of waves? Okay. So we can give examples first and then...
Can I give also?
Yes, please.
Mechanical waves require medium to propagate, while electromagnetic don't require medium to propagate.
Very good, very good. In other words, whenever you hear the word mechanical, just know that there's something like a medium involved. For example, when you're drumming, you hit that skin of that instrument there, you are hitting that drum. So in other words, we're having what we call a medium there. For example, the water itself, the water is a medium. So all the waves which involve disturbance of the medium, or where the wave must move in a medium, we call those ones the mechanical waves. Let me put that in writing here. So these are waves that require a material medium for their transmission. And then on the other hand, electromagnetic waves are waves that do not require a material medium for their transmission. And what this one means actually is that they can travel through a vacuum. That is what it means. They can travel through a vacuum. And examples of mechanical waves. Examples of these, there are very many. For example, we have water waves, we have sound waves. We shall see that sound waves actually require a material medium later on. Another one can talk about the water waves. Anything else that you can talk about here?
So the waves in a spring.
Yes, very good. Waves on a spring, a vibrating spring, in other words, all a rope, among others. On the other hand, the examples of electromagnetic waves, simply remember the electromagnetic spectrum. Do you remember those bands of the electromagnetic spectrum?
Yeah.
Yes, can you give me an example?
Sorry?
Examples of electromagnetic waves. And I'm saying that in case you can remember the bands of the electromagnetic spectrum, then you have, for example, X-rays.
Infrared, radio.
Microwaves.
Gamma waves.
Very good.
Radio waves.
All of those.
Visible light.
Very good. Radio waves. You can list all of those.
Gamma rays.
All of those. Visible light. We can talk about the gamma rays. Gamma rays are microwaves,
Ultraviolet rays.
etc. All of those. On the side of mechanical waves, you can even add on the earthquake. The earthquake is also a wave.
So they're called the seismic waves.
Yes, please.
Are those the seismic waves?
I'm not getting that word properly.
Seismic.
Okay, so we have as many examples as possible. And one thing that we need to remember always, it is going to be a trick. Let me just put it here as a note. That these travel at the speed of light. At the speed of light. That is 3 times 10 to the power 8 meters per second. So that is what you can say about these. There are very many other differences. We shall see them later on as we're concluding this. But at the moment, what we need is the definitions of each of these two, and of course, their examples. After this, we shall also be looking at what we call the transverse waves and the longitudinal waves. That will be later on, not now. Okay, now after this, we need to look at the terms used. Terms used. We shall consider a transverse wave. A transverse wave. So we have transverse. And then you have longitudinal. So look at this as well, maybe after the break. But at the moment, we have terms used in waves. You can draw this. I'll explain this again. This is how we represent a transverse wave. So among these, we can draw this diagram as well. And call this one, what name do you give to this part here? They talked about it in the video.
Crest.
Crest, very good. This part here.
Trough.
It's rough.
The trough.
Very good. How about the distance from this point to this point?
Wavelength.
Wavelength.
Wavelength. Lambda.
Wavelength. Lambda. Correct. Then we also had this part here. Someone is wearing pads. All right. So we have A. It is called the amplitude. A is the amplitude. Amplitude. Please draw this diagram because it's going to be very important. Then this part here is called the rest position. Rest position. Okay. It's called the rest position. So I have some 17 minutes remaining. Now, I'm going to explain this. You may not write down at the moment. I will send the PDF or the slide later on. But at least at the moment, I need us to remember this. I need us to remember this, that if we have a transverse wave like this, from the video that we have watched again, if you have a transverse wave like this, my diagram is not on scale, we're having particles of the medium, and all those particles are moving up. They're all moving up. But the medium itself is not changing position. We're also having particles that are moving down, like that. All these particles are moving down, and after they reach down, they move up again. In other words, When we are defining what a transverse wave is, this is the direction of motion of the wave. Direction of motion of the wave. And then our particles are moving upwards, all downwards. In other words, at right angles, 90 degrees. 90 degrees, like that. So how do you define a transverse wave, therefore? Transverse wave. We can simply say that this is a wave where particles of the medium vibrate at right angles. At right angles to the direction of motion of the wave. In other words,
So you can also say perpendicular, right?
yes, perpendicularly at right angles. In other words, perpendicularly. To the other word. So that's what we call a transverse wave. And examples of these are very many. Examples of these are very many. E.g., you can say that all electromagnetic waves. Electromagnetic waves. I've mentioned this already. All electromagnetic waves. They're all transverse in nature. Talk of the microwaves, the radio waves, the TV waves, the gamma rays, the X-rays, the visible light. All of those are examples of transverse waves. Another one can be water waves. Water waves. Waves on a vibrating rope. Waves on a string, a guitar, for example, string instruments. When you plug this,
Light wave.
light waves, all of those are under electromagnetic. They're all good examples there. So that is what we call a transverse wave. At the same time, we have what we call the longitudinal wave. A longitudinal wave, for example, I can draw this. We have, for example, a loudspeaker. These are air molecules. These are air molecules. For example, in case someone talks from this other end, the loudspeaker, like this. This is my, don't mind about my diagram. In other words, we represent a longitudinal wave like this. Like that. And on this one here, this region here where we have the molecules all together, molecules of air all together, most of them are concentrated in one region. That region there is what you call, this one here is what you call the region of compression. And then in this region here is what you call the region of rarefaction. Region of rarefaction. Now the distance between one region of compression to the next region of compression is the same as the distance between the crest and the crest. It's the same as the distance between the trough and the trough. In other words, it is called the wavelength. Likewise, the distance between the middle part of the rarefaction and the next region of rarefaction, that distance is the same. It is called the wavelength. We're going to define these ones more after the break. So, examples of what is a longitudinal wave, therefore. We can see these particles here, they vibrate to and fro. They keep on moving to and fro. And the wave itself moves in this direction here. That's the direction of the wave. For example, in case someone speaks to you, that someone is actually pushing the air in the atmosphere towards you. You can even try to feel it when you use your palms. Place them just before your mouth and then try to speak. you're kind of pushing the air molecules away from you. But as those air molecules go, they tend to come back as well. In other words, they vibrate to and fro. And the wave itself, which is this time around the sound, will be going away from you. In other words, as you're speaking, you'll be transferring the energy, the sound energy from you, going away from you. So longitudinal wave, longitudinal. How do we define them? These are waves. These are waves in which the particles of the medium vibrate in the same direction. In the same direction as the wave itself. As the wave itself. And examples of these ones here, we can talk about sound waves. We can talk about the earthquake. We can talk about waves on a vibrating spring. I'm just trying to rush here just because of time. Vibrating spring. Like that. Those are some of the examples of longitudinal waves. Those are examples of longitudinal waves. Yes, you can have that as well in the shortest time possible. He's saying that all electromagnetic waves are transverse in nature, and that is very true. But then, it is not that all mechanical waves are longitudinal in nature. That is wrong. That is wrong. For example, we have said that examples of mechanical waves include, for example, the water waves, mechanical waves. We've said that these ones here, examples include water waves. Water waves. But we see that water wave is actually not longitudinal. It is instead transverse. Another example of a mechanical wave is sound waves. But these ones are longitudinal. Longitudinal. Yes, so it is not that all mechanical waves are transverse or longitudinal. No, mechanical waves, for them, they are both transverse and longitudinal in nature. But on the other hand, all electromagnetic waves are transverse in nature. So that one, we need to know it before we go any further. All right. So, let's try to define some of the terms as we go for the snack time, the break time. Among the terms that you can define here, one of them is wavelength. Wavelength lambda. Who can define it for us? From what you have discussed and from the video.
This is the distance between two adjacent crests or troughs.
Very good. In that statement there, I'm interested in the word adjacent. But the most suitable there would be successive. Successive. In other words, it is the distance between any two successive crests. So you can write that as well. Make sure that you measure this word here, successive. Otherwise, in case this is our transverse wave, you cannot say the distance from here to there is the wavelength. No, this is wrong. It must be between one crest, one trough, and the next one, the adjacent one. In other words, the successive one. So it's the distance between any two successive troughs. Someone can define it like that. By the way, it has many definitions. One of them is that it's the distance between any two successive troughs. or it's the distance between any two successive crests, or it is the distance between any two successive regions of compression. Now remember about longitudinal waves. Or it is the distance between any two successive regions of rarefactions. That's another definition. All of them are correct. Any, you can state any. Or it is the distance. Or it's the distance between.
The distance.
I said something.
What of the distance between? No, the distance a wave travels in one cycle.
In one cycle, very good. Very good. That is very correct. It is the general definition. And that is what I actually wanted to say, but in a different way. You can say it like that. That is very correct. You'll be given full marks, or you can simply state it as the distance between any 2 points which are in phase. I wanted to comment about this one as well. Distance between any two particles which are in phase. Or simply put, like what Tamari has said, distance moved by a particle in one cycle. As simple as that. So let me explain what phase means. Assuming that we have a transverse wave like this. This is our transverse wave. And I can draw a line here, like this. And on that line there, we have particles. We have a particle here. This particle is moving up. This particle is also moving up. This particle is moving down. And this particle is also moving down.
So what was that definition again? Distance moved by a particle full wave something. Can you repeat it?
In one complete cycle. In one complete cycle. This is moved by a particle in one complete cycle.
Distance moved by a particle in one complete cycle.
Yes, that one there. Okay. Or distance between any two particles which are in phase. And I'm explaining what phase is here. Phase is like a complete cycle, in other words. So we can say that we have particles A, B, C, D. If you try to look at that diagram properly, you will see this, that this particle A is going to move through one complete cycle from here up to when it reaches there. That's like the distance, the wavelength, in other words. So if that is the case, then it means that particles which are in phase, these are particles which are moving in the same direction and are equidistant and are at the same distance. Same distance from the rest position. That is what phase means. Particles are moving in the same direction and are at the same distance from the rest position. For example, the distance from here to there. That distance is the same also for particles A, B, C, D, and A, B, C, D. But the particles which are in phase are only two. Particles in phase can be A and C. Also, particles B and D are also in phase. So that is what the word phase means. So the distance between this particle and that particle is what called the wavelength. And I'm stopping there for now. Shall begin from here after the short break.
Thank you.
Welcome.
So,
Thank you, sir.
I have a question. So.
All right, welcome back from that short break. Sometimes they call it the commercial break, the snack time. You're all welcome from that break there. All right, so far we have looked at some of the terms that we use under waves, and among these we say that we have the wavelength, we've seen the crest, we've seen the trough, and we ended by, I think it was Ayush was asking that, do we have wavelength as well in the transverse waves? And I said that yes, we do. And to make that point, or to drive that point home, I said that in case you have a transverse wave like this, whenever you see this shape, please always remember this is called a transverse wave. It is a diagram for a transverse wave. We have a displacement upwards, so we have displacement. And then even on the horizontal, you can have displacement all time, depending on the question. Displacement all time. So I've seen that this is called the crest. It is the highest point on the wave. The trough, I've seen that it is the lowest point on the trough. And then I've seen the wavelength. And I've found the wavelength as the distance between any two successive crests, that is under transverse waves, or to the distance between any two successive troughs, like that. And then this is transverse. This is transverse. And then under longitudinal, just a moment, Tamale and Marvin are back in class. Okay. So for longitudinal, we said that it is always looking like this. Whereby those lines there mean, they represent particles of the medium, molecules of the medium. So where the lines are very thick, that is what we call, they're very near each other, that's what we call the region of compression. Region of compression. And then where there are very few is what we call the region of rarefaction. Region of rarefaction. So in case you want to define wavelength in terms of the longitudinal wave, we define the wavelength as the distance between any two successive regions of compression. That is the first definition. Or you can still use that it is the distance between any two successive, or what are terminally called adjacent regions of compression, of rarefaction, like that. So this is rarefaction, this is for compression, and all of them work the same way. So another term that we're going to see is the amplitude. How do you define the amplitude? How do you define the amplitude? And from what we see here, and from the diagram that you've just drawn, we can define the amplitude as the maximum distance. It is the maximum distance of the particles from the rest position. In other words, in case you remember, we drew our transverse wave like this. So from the rest position, this is our rest position. Remember, we labeled it like this, rest position in our diagram, rest position. In other words, rest position is the position on the wave or in the medium where the particles are permanently at rest. The particles are simply at rest. They have not started moving. So the distance between the rest position and the crest is what we call the amplitude. Or it is the distance between the rest position and the trough, like that. So it has two definitions. It is the maximum distance that particles of the medium vibrate from the rest position. Or someone can say that it is the minimum distance, by minimum meaning that you're going downwards. Minimum, sorry, it is the maximum distance of the particles from the rest position. Yes, either way, or either moving upwards or downwards. Or in simple terms, someone can say that the amplitude is the distance between the rest position and the crest. Distance between the rest position and the trough. any of those can work. Any of those can work. Then, in a diagram still, I will say that in case we have, by the way, I did talk about this, that the size of the amplitude determines the amount of energy which is transferred. For example, in case I have this diagram like this, Ayush, what can you say about the quantity of energy being transferred?
So I didn't get your question.
I'm saying that in wave motion, a wave with a large amplitude carries more energy than a wave with a small amplitude.
Yeah.
So my question is saying that in that diagram there, what can you say about the energy being transferred?
So the energy is decreasing.
The energy is decreasing. Very good. In other words,
Yeah.
it dies away. So at first, since the amplitude is so high, then you can say that there is a lot of energy being transferred in this region here. But as time goes on, since the amplitude is reducing, then the quantum energy goes on reducing and reducing up to zero. In other words, in case you see this kind of graph, we can use a term. We shall meet it again under simple harmonic motion. We shall meet a term called damping. Damping. And it has a lot of applications, damping. A very good example is because if you're moving in a vehicle, you're sitting in a car, and all of a sudden the vehicle falls into a trench. It falls into a hole in the, on the road. If you feel the impact there and then what can you say about the springs of the car? Okay, we shall look at this later on.
But contain energy, so.
Yes, it means that the springs that they used are very weak. They're very weak. Or, in other words, if they feel the impact there and then it means that all the energy from the impact has been transmitted to you. Otherwise, in case you don't feel the impact there and then, in other words, you simply, if it feels normal, it feels like if you've not felt any impact, if the car falls into a hole on the road, then it means that the springs that they used are very suitable, they are very good. And therefore the amount of energy which was transferred from the impact at first was high, but then it has been reduced to a minimum. So that's what called damping. So I'll see it later on. So what you need to know from this point here is that the higher the amplitude, the more the energy transferred. Okay. Then, of course, in this diagram here, they're trying to show us what an amplitude is. I've explained that one already. This is the rest position, and the particles are permanent at rest, and then the amplitude is the distance between the crest and the rest position. Likewise, between the rest position and the trough. Any of them is fine. The wavelength, we have defined it already. We've defined this one already. The frequency, they talked about it in the video. What is the frequency? You can write the formula as well. I mean the definition as well. And not remind us, what is the frequency?
It's the number of waves formed per second.
Per second. Number of waves formed per second.
The number of waves that propagate.
Okay, yes. I'll add on the word complete cycles, complete waves. In other words, when someone says frequency, for example, I can put a statement that this person always frequents school. In other words, it means that the person comes to school very many times. In other words, the word frequency is simply about the number of something occurring in a given period of time. In other words, frequency is defined as the number of complete waves made in a second. The number of complete waves made in a second, just like Tamari has said, you can add on this. Complete waves or cycles. For example, in case I have this diagram here, how many cycles are there? Amun?
3.
3 cycles. Okay, let's check and see. So from here to there, that is why. In other words, you have a semicircle and another semicircle, meaning that a cycle is simply like a full circle. Then this is 1, 2. That is 1/2, 1/2. 1/2. So those are 3. So in case of these 3 cycles are made in 1 second, for example, here we have the time, and then here we have 1.0 seconds. It means that our frequency is equal to 3 cycles per second. And this one can give us something, that anything that is per time, cycles per time, in other words, the SI of frequency is called a hertz. A hertz, like that.
3 hertz.
3 hertz, yes. So, in other words, let me first show you this. Frequency can be found by counting the number of crests or troughs that pass through a point each second. We've seen that. Frequency is usually expressed in hertz, that is the SI of frequency, and that is a wave per second. And high frequency means more waves per second. In other words, the time is fixed, that is 1 second, but the number keeps on changing. The higher the number, the higher the frequency. And the less the number, the less the frequency. And then the low frequency means fewer waves made per second. Okay. Now, this is what I wanted us to note. In our books, of course, you can just simply give that definition there. Number of complete waves made in a second. And then the SI unit, you can just write this. SI unit is a hertz. A hertz, like that. The symbol is like this. Hertz. So, how do you get frequency? Frequency, let me just show you something here. You can just maybe write it on the side, maybe in the margin. We're defining frequency from the definition of frequency. From the definition of frequency, we're saying that frequency is equal to the number divided by the time. In other words, F is equal to number of complete cycles made in 1 second, like that. Now, if we divide this by n, divide by n, let me write it on the next page. This is the same as n out of t, divide this one by n, divide this by n. We shall say that this is the same as 1, divide by t out of n. In other words, when you get a given time, and you divide it by the number of complete cycles, for example, in the case we have this, those are 1, 2, 3 cycles. If those cycles are made in maybe 10 seconds, then we can say that for one cycle, the time will be equal to 10 divided by the number of cycles. In other words, for one cycle, we use the word or the letter capital T to mean the periodic time. Someone is asking something here, let me check it out. Because of the network, okay. So, in other words, this is the same as 1 out of capital T, where capital T is the periodic time, T out of N. Capital T, periodic time, is defined as the time taken to make one complete cycle. So what I needed to write, is this, that here we have complete waves. We have the SI unit, which is a hertz. We have already done that. Then simply write the formula that F is equal to 1 out of capital T. Out of capital T. You need to write this one as well. where F is the frequency, and then capital T is the periodic time. Periodic time. And note that capital T is equal to N, small t. When it comes to practicals, we shall meet this. T out of the number of N. Okay, yes, we're done with that. We're done with that. By the way, through. Okay. All right. So, after having looked at it, the frequency has. What is a has? We've already defined what
Mr. Hakim,
yes, please.
what is N in period?
Period, or what we call the periodic time, capital T. We're saying that this one is equal to small t out of N. In other words, we define period as the time taken to make one complete cycle or wave or oscillation or vibration. They all mean the same thing.
Okay.
Yes, a cycle, a wave, an oscillation, vibration, all mean the same thing. So periodic time is defined as the time taken to make one complete cycle. That's what I said. And from F equals to 1 out of capital T, we can say that our T is the same as 1 over F. So given one, you can find the other. That is what I need us to know as well. So
N is the number of cycles.
yes, N is the number of cycles.
Okay.
N is the number of cycles, complete cycles. Okay, a has, we have defined what a has is. For example, we're saying that a frequency of 1 has means that we have one complete cycle made in 1 second. One complete cycle, one wavelength, or one complete vibration, or one complete oscillation made in 1 second. In case you have 5 has, it means that there are 5 of them made in 1 second. I've already explained that. We talked about all of these ones, by the way. So I'm just reaffirming to you what we already discussed. Okay. Wave speed. How do you get the wave speed? Let me ask.
So can I try?
Okay, Ayush, define for us speed. What is speed?
Lambda times frequency.
Lambda times.
Okay, speed.
The definition. The definition.
Definition of speed.
Anyone?
So like normal speed or wave speed?
No, just the speed. Just speed.
Speed is distance per unit time.
Okay, all right. Distance by unit time. All right, okay, I can take that. In other words, speed is the distance covered in a given time. Speed is distance by unit time. All right. Now, we can also write this in our books there. As a summary there, wave speed. What is wave speed? Of course, we can say that from what Ayush has given us, that from speed is equal to distance out of time. We're deriving the wave equation, by the way, derive the wave equation. Derive the wave equation. So we're saying that from speed is equal to distance out of time. In case we have our wave like this, let's consider a transverse wave. And we have one complete cycle made. At this point here, we have our distance from this point to this point. Remember the distance made in one complete cycle. What name did you give it?
Wavelength.
Wavelength, lambda.
Wavelength, correct. Wavelength. And the time taken to make one complete cycle, the time t is equal to our periodic time, like that. Remember that periodic time is the time taken to make one complete cycle, like that. So from this expression here, we can say, therefore, that velocity, by the velocity is the same as speed. The only difference is that velocity is in a given direction. Remember, velocity is a vector quantity, speed is a scalar quantity. So this is the same as displacement out of time. So for one cycle, distance a wave covers in 1 second. All right, that's very, someone is defining a wave for us. Distance a wave travels in 1 second. So from, we shall say that for one complete cycle, or wave, our distance d is equal to the wavelength, our time t is equal to the periodic time, and therefore we shall say that v is equal to displacement, which is dense like this, then divided by the periodic time. In other words, v is equal to lambda times 1 out of capital T. And we can say that 1 out of capital T is the same as the frequency. Therefore, our wavelength, our wave velocity is equal to lambda times f. Therefore, you can say that v is equal to lambda f. You must be able to derive this expression. So I'm giving you some time to write that down. Then we proceed. Okay, I hope that we are through. Let's try out some numbers here. Okay. So wave speed at which the wave travels, in other words, the distance covered in 1 second. We've already talked about this. And maybe a note here, we can say that waves usually travel faster in liquids and in solids than they do in gases. Can someone give me a reason as to why for this? That waves usually travel faster in solids and liquids than they do in gases. Let's use sound, for example. Any explanation for this?
Sorry, can I give it a go?
Yes, please.
Can I give it a go, sir? In liquids and solids, the particles are closer together in comparison to gases. So that means the energy can be transferred from one particle to another faster as they're closer together. But in gases, they're spread out, so it takes a longer time for transfer of energy from particle to particle.
Very good. I can add nothing there. I don't have anything to add. But maybe to re-emphasize that, especially for mechanical waves which require a material medium for their transmission, it is always that waves travel faster in liquids and solids than gases simply because of the arrangement of the particles in that medium there. So solids and liquids, the particles are somehow close to each other. Therefore, it makes it easier for one particle to transfer energy to the next one. Otherwise, in gases, the particles are very widely spaced, and therefore it is kind of hard to transmit that energy. That is the reason for that. That is nice, Tamale. Okay. So for light waves, those ones travel in gases. They don't require a material medium for their transmission. So wave speed, we have done this already. We have just derived this expression, and expect a question from me that derive the expression of the wave equation. V is the velocity, lambda is the wavelength, F is the frequency.
Mr. Haki, may you please take back on the previous slide?
Yes, you're here. Yes, you may not copy.
Okay, thank you.
Okay. Look at sound in detail. When that time reaches, you'll be looking at all the factors affecting the transmission of sound waves. Okay. So we have also defined we have also looked at the wave equation, and I've said that I'll expect a question that show me how to derive this expression here. Derive it from first principles. Wave period, we have talked about this already. Periodic time, in other words, the amount of time it takes for one wavelength to pass a point in a wave. Wave is, okay, so I've said that the word period means the time taken for a wave to make, or just to make one complete cycle, in other words. Time taken to make one complete cycle, one complete wave. Okay, we have these questions here. Let's try them out together and we see what we know. So determine the wave speed of a wave that has a wavelength of 5 meters and a frequency of 4 Hz. This one has been done for us already. So from the wave equation here, we can see that wave velocity is given by lambda times frequency, and the answer is 20 meters per second. 20 meters per second. So we have that number one. Number one, let me change the color. Number one here. Okay. Number one there. So can I see stats of that number one?
Okay. Frequency is equal to. No, wait. Velocity is equal to.
Yes, I'm hearing.
Lambda, F lambda. So we have the frequency as 12 centimeters per second, which is equal to 3F. And
Yes.
we divide both sides by 3.
I beg your
And
pardon.
we get 4 Hz.
4 Hz.
The velocity is 2 centimeters per second.
Yeah.
12 centimeters.
And
Which
the
is
wavelength
equal to
times F.
is
Okay.
3. Yeah.
All right.
So
That's
F is equal to 4 Hz.
12 out of 2 or 3 gives us 4 Hz. Or we can please always look at the units before doing anything else. This is centimeters per second. This is in centimeters. So we can see that the centimeters actually cancel away. Otherwise, if the speed is in meters per second and the wavelength is in centimeters, always make sure that you use the same units. You change everything to meters. So this is the same as 4 Hz, or someone can say 4 per second. It is also correct. 4 Hz or 4 per second. All right. Yes, the next question is Ayush. Help us, number 2.
So the question says a wave has a frequency of 5 Hz and a wavelength, a wave speed of 18 meters per second. What is the wavelength? So we write the formula velocity equals lambda f. The wave speed is 18 meters per second, and so 18 equals lambda 5, lambda times 5,
which gives us our F here.
so lambda equals.
Okay, before you go any further, what are you calculating for?
We are finding lambda.
Yes, we are finding the lambda. All right. So shall we say that therefore that, not F, we say that therefore lambda is equal to 18 divided by 5, and what do you get? It will be
3.6. So yeah, the wavelength is 3.6 meters.
3.6
Yeah,
meters. Good. That is nice. I'm looking for another question here. Okay, before as we continue, let's also look at what you call the intensity and the intensity of a wave. Let me first press this one. Okay. So Tamale was talking about the seismic waves, the earthquake. Longitudinal waves, we have a question here. Okay, these ones you can all do them. Okay. You looked at light with Mr. Nicholas. Properties of light. Properties of light. I'm just giving, just by the way here, a review. We had one reflection. We had another one, refraction. We had another one, basically I looked at 12 of them, I remember. Okay, so when we talk about properties of waves, shall I look at this one in detail, maybe in the next lesson. Properties of waves, they're the same as the properties of light. And on this one, so you can add on diffraction. I know you have heard of reflection, you've heard of refraction. What you've not yet heard about is maybe diffraction and then interference. We shall talk about these later on. But all those ones are properties of waves in general. In general. Yes, let's try out that number in our end of chapter questions. Number 5, page 190. Yes, and I'll discuss this number for us. Number 5. Let me read it for you. It says that the diagram represents a wave on the surface of water at one instant of time. The speed of the wave is 7.0 centimeters per second. Calculate the amplitude, the wavelength, and the time period for one oscillation. Yes, that's the question. Anyone to take it on, you're welcome. You're welcome.
Yeah. So, firstly, we begin with amplitude, yeah? So, the total height with the waves and the water is 20 millimeter.
Okay.
Okay. 20 millimeter.
Yes.
Wait, what?
20 millimeters, yes.
20 millimeter is like 2 centimeter. And how is 9 centimeter bigger than?
It was a mistake.
Yes,
So,
sir.
it should, so I think it should be 20 centimeters.
So what
right?
unit is it, sir? 9 millimeters.
Oh, that is 9 millimeters. Okay.
It was a mistake, I think.
Yeah.
But in the textbook also, there's some few errors, like just after our first lesson. I think it's Tamari who asked the question. It was about the work energy, the work done in inelastic material. In the summary on the summary page, they made a mistake there where they wrote a half kx, which is the same as a half kx squared. So this one here was supposed to be the f. In case you check that page, on the summary page. So there's some.
Yes, a bit I was wondering there.
Yes, yes, there as well. So let's take this one to be in 9 millimeters. 9
millimeters.
Yes.
Yeah. So we can say that the the normal height of the water is 9 millimeters, and the height with the waves is 20 millimeters. So you first get the difference in which the wave is actually traveling. So the difference is 20 minus 9 is 11 millimeters.
Correct.
Yeah. So 11 millimeters. Now to find the amplitude, like 11 millimeters is like the crest in the trough, like full distance, yeah, from up to down.
Yeah.
So for calculating amplitude, we'll do 11 divided by 5. Sorry, 11 divided by 2. Yeah.
Okay, that is nice. That is nice. You can write that. You can write that.
To get 5.5.
5.5. So this is what you call the amplitude. This is also the amplitude. Correct. So 2a, now that is a plus a is equal to 11. So our amplitude is equal to 11 divided by 2, which gives us
5.5 millimeters.
Correct. Another person. Wavelength.
I think I've done a part, others can manage other parts. So
Yes, very good. Another part. We have done the amplitude. A is equal to 5.5 millimeters. Another person take on the wavelength. By the way, you can write in your book as well. There's no problem with that.
Can I try?
Yes.
So they're asking for the wavelength, and here we have like the 12 millimeters marked. So we should, I think we should first count how many complete cycles are there. So from this trough to this one, that is 1. So we have 1, 2, 3, 4.
From here.
No, from this side.
This side. So from here.
Yeah, to the other trough is 1 cycle.
If you can write on the screen, please do. If you can, if you can't, then let me write. But if you can, please do.
Okay, just a minute. Okay, so from here till here, that is 1 cycle. So now we're going to count how many we have. So that is 1, 2, 3, and 4. And this is like 4.5. So we have 4.5 cycles, and their distance is 12 millimeters. So if we want to find for 1 cycle, that is 12 divided by 4.5.
Okay. And the answer you get?
Is 2.67
millimeters. All right.
Yeah.
All right. All right. Yes. Hey, you have rubbed off again.
You wanted it back?
This is fine. They can get that. So, amplitude was 5.5 millimeters. Our wavelength, we've got, did you get 2 points?
2.67.
67 millimeters. That is correct. Another person take on the period. Anyone?
Me.
Yes, you are.
Wave speed is equal to length of a period, and we have the speed, which is 7.
If you can write, please do write on the screen.
Okay. Wave speed is
Yes, you can talk as you write.
over period. So we have the speed at 7 and the wavelength, which is 6.2. Wait, sorry.
12
I think
Yeah.
The seven is in
probably should
centimeters.
convert it
Oh,
because level is
okay.
in centimeter and
Yeah,
millimeters.
I think it should be
It's
like
70
millimeters per
millimeters
second.
per second.
Okay.
Yes.
Then over T, capital T. So our answer is 0.04.
Okay, that is nice. That is nice. In case you have computed very well, then that is nice. Of course, don't forget the units, that is in seconds as well. So the units here, we have millimeters, and then yet the speed is 7 centimeters per second. So 7 centimeters out of 1 second, you must change that one to 7 times 10, and then you get the millimeters out of the 1 second. So you get 70 millimeters per second, and that is what she has used here. That is nice. That is nice. That is good. So she's saying that from V is equal to lambda F. Since you're looking for the period, F is equal to 1 out of capital T. You can decide first of all get the frequency, or you can simply put it in the expression there and then like that. So this is the same as lambda out of the T, meaning that our T would be equal to lambda out of the velocity. Our T will be equal to lambda out of the velocity, which is the same as the lambda was, I think, 2.67, and the velocity is 70. You get the answer in seconds. Correct. Correct. That is nice. Let's have one last question. Number 4. Number 4. Let me just look for the question. So anyone to handle number 4 for us?
Can I try?
Yes, please, you're welcome. Please, you can write on the screen and you follow what you're doing.
Okay, it says on a copy of the diagram, mark a region of the wave which shows a compression label at C. Can you see it?
Yes, please.
I think that's where it is. Then part 2, it says a region of the wave that shows a refraction. Not so sure, but I think that's the one.
Okay. So you can simply write R and C, then R, like that. In other words, where you see the dots very close to each other, that is the compression. Where you see the dots far away from each other, that is the rarefaction. All right, that's nice. Any other person, part B? You can erase off that.
So can you give part B a go? The particle spreads out, moves away from the other air particles, then moves closer to them together during the compression and moves apart from the rest during rarefaction.
You can draw. Okay, the particle moves this way and this way as well. In other words, it vibrates to and fro. Why is it so? They're saying that shows some air particles of sound waves. And we say that sound waves are longitudinal waves. If they're longitudinal waves, then it means that the particles vibrate in the same direction as the direction of the wave. That is what we say. Then part C, the sound wave has a frequency of 240 Hz. Explain in terms of movement of an individual particle what this means. What does this mean?
The 240 complete waves per second.
All right, as simple as that. The particle makes 240 complete waves. You can say waves, you can say cycles, you can say oscillations, you can say vibrations per second. Very good. And then lastly, the waves, the speed is at 20 meters per second. If you take the wavelength from V is equal to lambda F, you can do that. You have the frequency, you have the velocity, you can get the wavelength. All right. In the 3 minutes remaining, I want us to look at page 182. Page 182 as we summarize our question here. Page 182. Have I passed it? Okay, not yet. Page 182. And I want to talk about this. What is the meaning of the word intensity? How do you understand it, intensity? Intense. Okay. I can just refer to light.
Relate to focus, I think.
I beg your pardon, Tamale.
I think it can relate to focus, like how focused something is or how concentrated something is.
Very good. I just pick out only one word, concentrated. That's what I'll pick out, concentrated. In other words, in case I look at, for example, light, in case I talk about the intensity of light, I may simply refer to brightness. The higher the intensity of light, the higher the quantum of energy at a given point. In other words, the higher the brightness. So, we're saying that in wave motion, the intensity of the wave generally decreases as it travels along a given medium. And the two reasons for this: one, the wave may spread out. For example, in case this is our water, you throw a stone in the middle like this, the wave spreads out like that's what we call spreading out. And another reason is that the wave may be absorbed or scattered by the medium itself. In other words, that energy may be used up to other forms. Okay. Now, if that is the case, then how is intensity related to the wavelength? I mean, the amplitude. That is what this part is all about. And because of that, we can simply quote and say that you can simply quote and say, go down, that intensity is proportional to the square of the amplitude. Intensity is proportional to the square of the amplitude. In other words, I is proportional to S squared. And in case of remove that proportionality, we can simply say that I is equal to a constant K times S squared. Now, if you remember something about Hooke's law from there, yes, please.
So I think we've missed something. If you could scroll up a bit. So.
If I could scroll up.
You missed the introduction. Because I see there's a formula there.
Oh, okay. I have 1 minute. Just hold on. From F is equal to KE. From F is equal to KE. From F is equal to KE, we say that K is equal to F out of E. In other words, it means that we'll get F1 out of E1, get the same as E2 divided by E2, get the same as when you have Fn out of En like that. Now, when we come to this, we are going to use the same expression in the calculation. This is what I mean. This is what I mean here on the next page, for example. This is what I mean here. That in case you have intensity being equal to Ks squared, you can have your constant K being equal to I over S squared. In other words, this one here means that I1 divided by intensity squared 1, you get the same quantity as when you have intensity 2 divided by amplitude 2, but you square it like that. Now, I wanted you to try out this question here. And we've been given two quantities. One is the amplitude, A1, and its intensity, I1. So I'm going to use the same expression as this and look for the other unknown. So you can try that out now. Otherwise, I'm stopping here. See you in the next lesson. Next time. Okay.
Thank you.
You're welcome. You can.
Thank you, Mr. Hakim.